let's get started. The first speaker of the afternoon session is Willie. He's going to give an invited talk about coherent cosmology with FRBs. Let's welcome Willie. Oh, okay.
Okay, thank you. I'm going to talk a little bit about the application of FRBs, and we heard today that there are two types of things that people do with FRBs to understand what they are and to use them. This is definitely a discussion of what to use them for. And there's one aspect of it that is very little discussed, and I feel in science, just the practical consideration when you work on something, that I do when I think I work on something, is to look at the potential and then the number of people doing it. For example, dark energy, there are tens of thousands of people doing it, and even though it's a big prize if you get it, there are many people who are competing with you. Whereas there are other directions that I feel have comparable promise that almost nobody works on except for Dan. And that's this scintillation propagation. So I strongly encourage, especially young people, to think about the things that not everybody else is doing, but have even higher impact. Okay, so this is what I just want to, to stress. So to think of the things that is forgotten and is yet unavoidable. And that's the fact that FRBs are coherent radiation. So just maybe I'll just jump over that. That's actually not that interesting. So we saw, in fact, Dan did point out that in Thornton et al., that pulsar FRB he showed, you see this effect of scintillation. Let's see if there's a pointer here so you can see. And you can see in this little inset that some frequencies are brighter and some frequencies are fainter. And if you look at Thornton's picture in hindsight, it clearly was there. They didn't say so. They didn't quite stress that. So they didn't get credit for not having looked at it in that way. Whereas in Xiaoxian's event that Xiaoxian here discovered, what we actually did is measure and quantify the scintillation properties of an FRB, the first ever published, and perhaps it's one of probably only two published things on the scintillation property of FRB. So again, I encourage all of you to look at these data. People, do all kinds of complicated things when these are straightforward and teach you so much information that you can learn about the properties. So we heard from Dylan earlier today and from others that this has ruled out a large number of classes of models. For example, people were discussing that intergalactic medium might cause scattering. That's ruled out because if that were to happen, you wouldn't see the scintillation from our galaxy. Okay, this is probably one of the strongest influences and constraints we have, and it's not being, not used much. So think about these. It's not actually that hard. Dan gave a very nice introduction as to how that works. You can measure what's called the scintillation bandwidth, which happens to be a few megahertz. At the lower frequencies, it's a strong function of frequency, so it's consistent with the Thornton kind of scales, which were more like tens of megahertz, but at twice the frequency. And again, J.P. McCart, of course, is our late colleague and a friend of mine. He not only had a FRB plot, which is much talked about. I actually think the really fascinating work he's done is on VLBI imaging of propagation. So here I show a picture made by Daniel. See? Daniel's not here today. Okay, anyways, Daniel, who's not here today, made this plot of a reanalysis of the VLBI image of what a pulsar looks like on the sky when you use the coherency to make VLBI. And the reason I say coherency is, if you just normally ask what's the resolution of a VLBI image, you get lambda over d. You take a wavelength of a meter, which is what this was made of, and the Earth is maybe 1,000,000 meters across, and you would get, say, 0.1 arc seconds as your resolution. This one gets you 0.1 million. This one gets microarc seconds. So about a factor of 100 better than naively you would expect, because it's a coherent radiation. Okay, these lambda over d arguments can be overcome by orders of magnitude. So this is the most precise image that I'm aware of. Okay, it's a black hole image, 50 microarc seconds. This is 10 microarc seconds. Okay, high resolution. So when you think this black hole is high resolution, it's child's play compared to what you get from coherent interferometry. Okay, these are all things that I think people, I just mention these because it's not mentioned anywhere else. You don't hear that much. So there is this revolution that has so much information in it. It tells you what's happening between you and the source at this unprecedented accuracy. It raises these questions. Why do the lensed images all appear on an almost straight line, but not completely straight, a wiggly line? What's going on? Okay. And FRBs do the same. To think of, keep that in mind. These are things that, are very prominent features. This is not some subtle effect. This always happens for pulsars and for FRBs. Another thing that you can do with pulsars is you can try to use this scintillation to use it as a telescope to measure the surface of the FRB. So in this case, it's the surface of the neutron star, and you can see that you can measure things on the resolution of kilometers. Okay, sure, this is only a kiloparsec away, not a gigaparsec. But this sensitivity is independent of distance. So if you want to know what's happening at a kilometer scale in an FRB, here, there are tools. Okay, I'm just want to throw these out. These are all things that don't get talked about much in the FRB world, or for that matter, even in the pulsar world, because these are relatively new techniques that Mark Walker and JP and others pioneered. And I just want to, advertise that there is all this great amount of information that we should exploit. Okay, I don't think we need to all do exactly the same thing about. Even though sure, dark energy, dark matter are good questions, but these are the tools that may have a much higher constraining power. So, and of course, we have the experts in the field in the room here, like Dylan did a lot of these analyses. For example, with microlensing, it turns out that Matt, we heard a talk already today that dark matter, I think Simon gave a talk, that dark matter may cause microlensing. Well, stars definitely cause microlensing, and stars definitely exist. Okay, I think that's not optional. And then to think, how can you measure all these things? And it's not as trivial because, as Dylan showed, you have to pick out the microlensing in the presence of plasma lensing. Okay, so these things are more subtle than it requires some thinking, and so it's a new regime that one should think about how the data actually works and what's observable. Remember, this is coherent radiation that forms interference patterns, whereas in astrophysics nothing else forms interference patterns to speak of. So keep those things in mind. This is why FRBs are exciting. You've got a coherent source at cosmological distances. So for example, because you can measure time delay to nanoseconds, for example, chime or burst sample electric field at 1.2 nanoseconds sampling rate. So if a delay of 1.2 nanoseconds is an order 1 effect, and you can measure delays between echoes of an image and the image at that level. You can measure delays, flux ratios, so modulo distance degeneracies. You can instantly know the mass of your lens, whereas in traditional microlensing, you have to wait for several months for your backward object to get brighter and fainter, and then you only statistically know the mass of your lens, which depends on velocities and other things. FRBs, you don't have to repeat, they have to go off once, and you know everything that you would have otherwise had to spend years and years on doing, and still wouldn't know. Okay, so these wave phenomena can carry a huge amount of information that, again, I encourage people to think about these very unique aspects. These are the regimes, 99% of FRB papers, they haven't thought about it. I think it's pretty clear. In addition to that, the micro lensing is a fairly simple, straightforward application, good to think about, easy way to get used to what happens. In reality, there are other lenses, cosmological gravitational lenses and plasma lenses that are known to exist. They cause the scintillation that we observe and the scattering that we observe. And just like you can use gravitational lenses to measure distances, there's nothing particularly special about gravitation. Any lens is equally good for measuring cosmological distances. You just need to know something about your lens. Okay, you have to measure an angle and a time delay, and you're done. So being gravitational lens is, it's what people have been thinking about for the last 50 years. But here we have sources that are known to plasma lens. Here's some forecasts we made with coherency. Anyways, Dylan can tell you all about catastrophe theory that may allow you to have a small dimensionality of what lenses can do. And I'm actually going to summarize here that I think we should, all of us for FRBs, take to the advantage that they measure certain things 1 billion times more accurately than anything else. So time delays at a nanosecond. People who do traditional gravitational lensing, they're happy if they can get a time delay to a few hours. A nanosecond to an hour is 10 to the 12. Okay, so this is, I don't even know what the word is, trillion is only 10, trillion I guess is 10 to the 12. A trillion times more accurate in time delay measurements than traditional techniques. So this is not a small number. And a lot of things that, when you have such a big change of fidelity, gives you access to different information. Thank you.
Questions, comments, please? Okay, please. Jennifer?
Thank you, Willie. Actually, the third point you show on the conclusion, I wonder why is it kind of modeled as a 1D feature, not 2D or 3D in terms of plasma speed.
Oh, it's just the fact that the image you saw, sorry, I can't put my screen right now, is that the images are all in a straight line, and that's only possible if your lens is 1D. So it's a measurement.
I see. Thank you. Thank you.
Any other questions, comments? Anyone from online? That's fine.
Thank you for a very interesting talk. So, if we really want to go to this direction, so what kind of the FRB telescope will be the best to do this?
Well, you need, I think you need to cover a wide range of parameter space because the plasma effects are very frequency dependent, and then if you have repeaters, you get a lot more information. As we heard from Dylan, you want this time variation, so you want a telescope that's efficient at finding repeaters. Burst, for example, is perfect at finding repeaters because you expose the whole sky 12 hours a day, every day.
Yes.
So it depends on which aspect. Whereas for other things, if you want, cross-section to lensing, you want to go deep. You want to use a fast telescope. So those will find the furthest away sources, the biggest telescope.
I see. Thank you very much.
Any other question, comments? Okay, if not, let's thank Willie again.